Good afternoon, ladies and gentlemen. And first of all, I really appreciate this opportunity to come and talk here. And thank you. And it's also very exciting to see a lot of students, professionals, and everybody interested very much in this energy topic. And what I will cover a little bit about the power systems end of energy and how renewables are being integrated, and then what kind of solutions in terms of research that we're working on at North Carolina State University. So that leads to my title here on power distribution system modernization using solid-state electronics or power electronics and integrated renewables. So first of all, I would like to start talking about some of the trends in the power and energy area. You may be familiar with many of them, but I want to highlight what's going on in this domain here. So I'm sure many of you have heard microgrids versus macrogrids. So by definition, the definition is up there. Microgrids are like localized grids that can disconnect from the system to operate autonomously. So that's the key word. On its own, it can work and help migrate the disturbances to strengthen the grid resiliency. In other words, or in simpler terms, microgrids is a composition of the load, the generation, and storage, and all those things being connected. And the main objective is, in case of disturbances or outages, these microgrids should be able to provide us with reliable and resilient power. So as shown in this diagram here, which I obtained from the DOE website, microgrids can be small or large. So here it's just a single household can have a solar PV generation connected to power his or her household, and that's a microgrid. And then it could be very large on the other extreme where it connects all the way up to the substation level, and including these features, it could also be a microgrid. In some countries, they're also known as like nanogrids, where it's smaller, just even as small as like 500 watts or 1 kilowatts, or even smaller, providing a single household in developing countries. And these are like the nanogrids that are connected together. So that's one of the major trends in the power area that is going on. So moving on, the debate between AC versus DC, those of you who are in electrical engineering know the issues of the fights between Tesla and Westinghouse about whether to have a DC system or an AC system. So that talk has revived. And that's because of many of the technologies that are being developed now that enables a DC system. So large ships that has DC distribution systems, electric vehicles, a vehicle has its own generation in terms of its power plant, internal combustion engine, or a battery-powered source. It has its battery, it has its loads. So that's a microgrid, an electric vehicle powertrain in itself, and it's a microgrid on wheels. HVDC, high voltage DC transmission linkages, are used for improving the capacity, and also when the system is long enough to reduce the installation costs. And in our homes and everywhere, the DC loads are everywhere. All of the gadgets that you use, your phones, computers, everything actually runs on DC, even though we power them with an AC, 120 volts or 110 volts, and then use some electronics to convert that to DC. So if you take your television, which now is connected to 120 volts AC, you can easily connect it to 110 volts DC, and it would run just fine, no problem. So most of the things that we use are actually using DC, and then we are converting and then losing power or because of the efficiencies of those power conversion stages. So solar panels, they generate DC. Wind power systems, they generate AC with the AC machine, but then again, you use the power electronics to convert it to DC, and then again, to connect it to the AC transmission system, you use another converter to convert the DC into AC. So we have all these unnecessary power conversion stages. Data centers is another big example where a lot of these power conversions take place, and the data centers are a huge consumption of power load. So the DC systems inherently rely on power electronics. In this talk, you will hear a number of times about this power electronics, and that's a key enabling technology. And in the talk, you'll see the progressive inclusion of power electronics and how it's helping us with the systems. So then energy analytics, so driven by large corporations like Walmart, or which are the biggest, the chains in the US and spreading into the world also, Food Lion, JCPenney. They want to manage a portfolio of large portfolio of sites, right? They have a lot of data, they want to collect them and manage them. So energy organizations like SAS, IBM, and the IT organizations like SAS and IBM and others, they are now in the business of analyzing this data. And in the power sector, we also have a lot of data coming from the technical side of things, many nodes in power generation, as well as customer data in terms of their usages and when they use it. So there is a whole host of data giving rise to these energy analytics, which can actually help us develop systems and algorithms, for example, demand-side management. So energy analytics is another area where there is a rapid growth and expansion. Then another thing that is also coming up is transactive energy. So by definition, the transactive energy is a set of economic and control mechanisms that allow to balance dynamically in real time the supply and the demand, where the user can also participate from an economic perspective. So, for example, if I'm a homeowner that has some solar power generation, I can feed that. When I have excess, I can feed that back into the source, but in return, I should get some benefit in terms of financial. So that's what transactive energy is, and this is another area that is also rapidly expanding. So another technical area, this is relating to the power electronics, is the development in the wide bandgap semiconductors. So this is going deep into the electrical side of things. So power electronics converters that converts AC to DC, DC to AC, and vice versa, and other things, they use these power electronic devices. And currently, like the transistors or MOSFETs that are used in computers and everywhere. So currently, they are all based on silicon. But the next generation ones are going to be based on another material called silicon carbide or gallium nitride. And they use the wide bandgap to store more energy in a smaller, more compact form. So what these wide bandgap devices are enabling us, like they're pushing the electricity, the voltage, the frequency, the current, the temperature at higher levels within a smaller footprint on size. So that enables us to develop these power electronic converters in a much more smaller, compact form. And not only the device themselves are of higher voltages and current ratings, but because they operate at higher frequencies, the other bulky components that you need in a system, like the capacitors, the inductors, and the transformers, their size shrink also. So overall, you have a much, much smaller system. So the only thing that is holding us back using more of these silicon carbide and gallium nitride devices are their cost. But the cost is coming down, and they're slowly entering into the market. For example, silicon carbide devices are getting into the electric vehicles or hybrid electric vehicles because any size and weight reduction that you can do in an electric vehicle translates into a few more miles that you can go with the same energy storage in the battery. So that's like helping us in alleviating some of the range anxiety that electric vehicle users would have. So leading to that, from wide bandgap semiconductors in electric vehicles, the electric transportation is also going through a revolution here. As we can see, more and more electric vehicles are coming in. So even like if I go back 5, 6 years ago in the US, the pure electric vehicles or the battery electric vehicles didn't seem that much near. It was more like the hybrid vehicles, like the Toyota Prius, that was more in the trend. But it changed drastically over the past few years, and now all of the auto manufacturers are offering these electric vehicles. So the growth, again, in the US is not so much, but it's the largest growth is in China, and then probably in Europe, and then in the United States. But there are key market drivers that drive the usage of these electric vehicles. And the three market drivers are the energy diversification. We need to move away from depending so much on the fossil fuels, and we can diversify using renewable energy to power these electric vehicles. So that's one incentive. There's economic growth, like because of the electric vehicles and the expertise needed, so workforce needed for those. So that helps with the economic growth, job creation, etc. And then, of course, addressing the environmental concerns that the electric vehicles can help us. But of course, like just a direct conversion of an internal combustion engine vehicle into an electric vehicle and using fossil fuels to generate the electricity doesn't help. So we have to be responsible as like migrating to electric vehicles is not enough. We have to use more clean energy sources to power these up. So then going in that direction is there are other increased opportunities like autonomous vehicles, increased telematics within the vehicles, and developing lightweight electric machines, and energy storage costs are coming down. So there are opportunities that can contribute towards these from many different aspects of engineering. And then electric vehicles, I bring this here because the electric vehicles, electric transportation and the power systems are connected at the hip, right? Because you need the charging stations, which affects the power systems, and the utilities have to upgrade their power systems if we have more and more of these electric vehicles to charge these vehicles. So Electrify America, which is a subsidiary of the Volkswagen, is going to invest $2 billion over the next 10 years in installing infrastructures like charging stations for the promotion and growth of electric vehicles in the US. And the middle one shows you the growth rate of these electric vehicles. And it's not just vehicles. In many other countries, it's electric bikes. There could be many different forms of the electric vehicles that you will see in the market. Like here showing a picture of a bus, an all-electric bus. This is the Tesla crossover vehicle, which on a single charge, if one can afford, the most expensive one can go like 250 to 300 miles on a single charge of that vehicle. So going from these trends here that are shown at the top over there, okay, let's see what are the technical challenges that are related to the electricity markets and the electricity generation and storage. So as it stands, the electricity grid is based on centralized generation. We generate electricity in a central power plant and use long transmission lines, and because the load centers are far away, like the homes and the commercial buildings, and then we distribute again at the load center. So it's a centralized generation going over transmission lines, and then this being distributed at the load centers. But what is happening also, the cost of solar is coming down drastically. The cost of batteries are also coming down. And in addition to that, there are these natural disasters and other sort of disasters that is causing disruptions to the supply of the electricity. So the reliability becomes an issue. In situations where the grid may not be that strong, so any disturbance would take a part or some part of the grid out. So that causes reliability issues that we don't get power supply all the time that we need. So one of the pictures here is shown for the Superstorm Sandy, which took place in New York a few years back. And there was electricity outage for several days. And that prompted the New York government to provide policies or to develop policies that would encourage developers and others to install microgrids to address this resiliency and reliability issue. And the microgrids enable going from a centralized generation to a distributed generation. So that is another trend that, like, if we install rooftop solar in residential homes, or light commercials can also install solar panels in their rooftops. So we are going towards where the customer also is a source of generation. So it can be renewables, it can be other sources of generation, but it can be coded into distributed generation. So that's one of the major trends these days. We're going from centralized generation towards distributed generations because of the opportunities and the technologies that are available with renewables, and plus also we want more secure and reliable power. So that's the other incentive for going towards distributed generation. So where I come from, as you've heard in the introduction, from North Carolina State University, where we have an engineering research center. We call it Freedom Systems Center, which stands for Future Renewable Electric Energy Delivery and Management System. So this is a National Science Foundation sponsored center, and the focus is to address a grand challenge problem over a long period of time, like 10 years in this case, to develop technologies that will enable developing a modernized power grid. So the grand challenge problem that we are addressing is modernization of the power grid, looking from the power distribution side, where we are integrating renewable generations and then other controls and power electronics to make the system more reliable and dependable. So what is an engineering research center? I'll give you a little bit of a background here. So the Freedom Engineering Research Center is a Generation 3 ERC established in 2003. It's a 10-year, $40 million investment by National Science Foundation, which is the federal agency supporting research in the universities. And we are addressing the grand challenge problem, as I mentioned here. And we work with industries and other partners in developing technologies as well as educating the workforce. So each center has three major components: the industry, research, and education. So we partner with industries who are members of our center to help us define the problems and also help us steer us in the right direction for research that we do. And there are graduate students as well as undergraduate students who do research in the key areas of focus. And then there is an education part, which is educating not just the college students or undergraduate students and graduate students, but below, like from middle school students to high school students, so that we have a pipeline of students who get motivated in going into science and math so that they can, again, contribute towards society in this sector of technology. And NC State University is the lead for this center, but not the only one. We have partner institutions like Missouri University of Science and Technology, Arizona State University, Florida State University, and Florida A&M University. And we also have two international partners, the ETH from Switzerland and then Aachen University from Germany. So our grid modernization model is parallel with how the internet evolved. So as if you recall, we use the web and the internet every day, and then it also started with centralized computing, the IBM mainframes, as you can see. But now the computing is ubiquitous. We all have computers that get connected to the computers. So it is distributed computing. And what has helped the entrepreneurship and the innovation ecosystem is to come up with all these companies like Google and Facebook and Netflix, which was not even thought of when we were developing this internet system, right? So similarly, now we are moving from centralized power generation to distributed generation, and we don't know what kind of businesses we will evolve in the future in the power and energy sector related to the things that I mentioned earlier, like transactive energy or energy analytics, centered around power and energy. So there was a paradigm shift in the computing industry. So similarly, the power industry is also going through this paradigm shift, as I mentioned, going from centralized generation to distributed generation, enabled by the renewables, the battery technologies, and the loads like electric vehicles and other DC loads in our systems. So we don't know, but we can expect there would be a lot of entrepreneurship and business opportunities. So that's not for us engineers. We develop the technologies, and it's all for the business and the policy people to look for these other opportunities in terms of entrepreneurships. So that's where we model our system and call this an energy internet. So in this energy internet, we will have a microgrid which has these three elements of load, generation, and storage. So let me explain in a little more detail of what that system could look like. So if you think of the medium, so we are on the distribution side. We're discussing about which is at the medium voltage level and lower. In our homes, we get our power supplies in 110 volts or 220 volts, but at the distribution transformer near our homes or in the commercial installations, they come at 480 volt AC. There are variations of that, of course, depending on the region and all that. And there is a transformer that converts the medium voltage, it's 12 kV or 33 kV, into that low voltage. So that's a distribution transformer. So what we are proposing here is utilizing the revolutionary power electronics technologies to replace that traditional distribution transformer, which is made of iron and copper, which is dumb, doesn't have any intelligence, with these power electronics-based transformers where we can have intelligence, where we can have connectivity with other components in the system, and then build a solid-state transformer with these communication comlinks and build this network. And another thing that this will help, because this is a power electronics-based technology, we can have both a low-voltage DC output or a low-voltage AC output to help either build a DC microgrid or an AC microgrid, or a DC distribution system or an AC distribution system. So in the future, we may not even need an AC distribution system. It could all be like a DC distribution system. And also, we need protection devices, so that's what the circuit breakers and other components that can isolate systems in terms of failure and other issues. So using this revolutionary power electronics along with intelligent controls for both power management, energy management, and fault management, we can make this system work and enable the market penetration or participation of these microgrids, where as a customer, as a homeowner, I am not only receiving power in one direction and paying the bills, I can also participate in that market on energy considerations or power flow considerations, on economic basis, on social considerations, or also on security considerations. So all of these things, I can be, as a customer, be an active participant in this whole system. So that's what the system is evolving towards. So this is another picture showing the same system. If you think of the sub-transmission level power coming in, and this could be the Freedom system, and these are the transformers that are connected to, let's say, a few homes, and within those homes there can be storage, there can be some local generation, and the loads connected to it. There could be other systems like this. It could be a commercial system over here, but they are all connected through these distribution transformers and these fault and protection devices. So what these intelligent transformers can do is, in case there is excess energy in this area, they can transmit power to the other ones, or vice versa. And in that way, they can minimize the variability of the power generation that is coming from the centralized sources, and then enable a system that can be much more resilient. In case this central power plant goes away, okay, this should be able to sustain within its own generation for at least, depending on how the system is designed, for several days or weeks, and be self-sustaining, giving us a reliable and secure system. So the freedom system can be a small, consisting of one solid-state transformer and a load. And DGI is the intelligence. We call it the distributed grid intelligence. We can add some renewable sources over here or some storage devices to enhance the reliability and the resiliency. And we can add another more of them so the system is scalable, connected to the distribution feeder. And then you can have some local area networks connected to it. And we would, if the system is getting bigger, then we would install some intelligent isolation devices or protection devices into the system. And then they all can be connected to the enterprise through some SCADA, and enterprise softwares and ancillary services can be provided with the help of these communications and connection systems. So the concept is like the traditional grid or the legacy grid. The way it's developed is based on like the things that I was mentioning: centralized generation, one-way power flow. It's a static system. It's an AC-based system. It's a hardwired system, and then there is limited opportunity to introduce renewables because you cannot just add on to the existing system without disrupting its stability or performance. So those things needs to be carefully evaluated. And then like the security systems are also like an ad hoc. So looking into the future, if you go, what we are looking into is more distributed generation and storage integrated with storage. The power flow can be two-way. There's intelligence so that it will enable the introduction of other services, other facilities. It can be reconfigured to address like failures or some disasters. We can use AC and DC both. It should be a plug-and-play type, just like we plug-and-play things into our computers. It uses solid-state devices so that instead of electromechanical devices, so that the components are smaller and more efficient. And it will also enable the increase of the renewables, a high penetration of the solar or wind. And the communications bandwidth also should be enough to enable us these interconnections between the systems. And the system security, which should be both cyber as well as physical, would be embedded into the systems. So the solid-state transformer, not only being smaller, lighter, compact, it gives several other advantages. For example, it is current limiting in the sense that it can protect its own. It can buffer the system. Like a traditional transformer, the input and output are fixed by the turns ratio in terms of voltages and currents that flow through. But with this solid-state transformer, you can actually buffer the input side from the output side. It can limit its own current. If there is a fault on one side, it can isolate that fault. It can quickly connect or disconnect. It can provide us with the power management, for example, introducing reactive power or power factor, help with demand side management. It can help, like in case there is a fault, low voltage ride through, so the voltage dips, but the transformer controller can handle that, and it should be able to ride through that fault. And then at a higher level, it can do energy management, like introducing or connecting to advanced metering infrastructure or demand side management or dispatch controls. All of these can be very intelligently managed by this solid-state transformer. So I'll not go a lot into the details of these solid-state transformer, but this is just a circuit to show how it looks like. It's an electrical circuit made of these power semiconductor devices. So here it's showing a silicon carbide, the wide bandgap semiconductor MOSFET at a higher voltage. One device itself going up to 15 kV. And this is on the low voltage side, 1200 volt, 100 amp. So this end gets connected to the medium voltage side, and this end is providing power to 240 volt or 120 volt split phase. And in between you have the DC. So DC can be supplied from here. Here there is a transformer, of course, like the regular transformer. But because it's operating at higher frequency and with these devices, it's much, much smaller and much more compact. So in our center, we have developed like up to third generations of these solid-state transformer. This is another improved version of that, and this is showing how it's enclosed in a box just to replicate from an AC input to an AC output a traditional transformer that is ready to be installed. So going one more step, showing the efficiencies that can be achieved through these, and these are experimental results that we have, where gradually from generation 1 with 90% efficiency, we have moved up to go up to like 97% efficiency of these transformers. So one key difference with traditional transformers is like the traditional transformers are designed to have their peak efficiency at the maximum load level. It is very inefficient at light load conditions. But these electronic-based transformers can be made to be efficient from light load to full load conditions. The other major component is the fault isolation device. So it uses a fast electromechanical switch in series again with a solid-state device. And the reason for using this fast mechanical switch is like mechanical switches can be very low loss, and through electromagnetics we can make it operate very fast. But when a circuit breaks, there is arc, so how to handle that, that's an issue. So here we are again using silicon carbide type devices to handle these arcs in those fault isolation devices. So this is just a picture of showing like what we are developing and what we are trying to replace. So this is this typical distribution transformer that you may have seen in the pole tops over there. And gradually we're reducing the size of these power electronics-based transformers from generation 1 to generation 3. And similarly trying to replace those mechanical slow circuit breakers with those electronic plus electromechanical hybrid type circuit breakers. So another area that needs a lot of attention is like we're introducing these power electronics to wind generation systems or solar generation systems or through these freedom systems using power electronics. So they provide us with a lot of advantages, but at the same time, they introduce a lot of problems also because they switch at very high frequencies, and you cannot randomly just connect a wind generator or a solar generator into the grid anywhere. You're going at the systems level where there are lots of other generation in the system, other loads, and it's a whole group of components and loads that are working together to keep the system stable. And by stable, I mean like we should always get like 110 volts here at 60 hertz. If there are variations of that could either blow up, go in one direction, or collapse to zero, right? So that's what I mean by stability. So when you have power electronics, one thing it does is like, let's say you introduce solar, it's taking away the inertia of the system like provided by the large synchronous generators. So that destabilizes the system. So analyzing, modeling, and coming up with control mechanisms that will maintain the stability of the systems is very critical, and that needs to be evaluated before you introduce new technologies into the system. So there could be like, as you connect a power electronics device, there could be oscillations starting in the system that could eventually blow up. So those of you who are studying controls or in the controls area can relate to that. Oscillations that grow can lead to system collapse. And these power electronics-based components have the potentials to do that. So system controls is very important. So two things that we need. One is analysis and modeling techniques, tools to evaluate the system, because these systems, as they scale out, they can become very large. So for these large systems, how do you develop suitable models? That's one issue. And then the other issues like the controls, the stability. So always the generation has to match the load, and that is related to the stability. So our work is based around 3 levels of controls. One is at the component level. We call this like the local controller. And then when they interconnect, then we have these intelligent power management controllers that work at the system level to ensure the power balance, as well as to avoid stability issues. And then at the highest level is the energy management controller that can take like user inputs or forecast data, weather data, and then optimize the energy usage of the system. So this is a simple diagram trying to show that we have this power electronics, and then here it could be the solar panel or generation, making up the system. And for modeling, we can simplify these things in terms of like a active source here, and then some impedance. So what this component says as the rest of the system is some impedance with some power generation. But think of it this way. This is not a traditional load where it just consumes energy. It's an active source. So these controllers are all active. So that's why they would interact with the rest of the system. And that's the need, that why we need to have good control mechanisms to make sure that the system remains stable. So these days, the solar penetration levels are low. For example, in certain parts of the US that we live in, it's less than 10%, right? So with low penetration levels, it's not a problem. The system remains stable, and the grid that it connects to still remains strong. But when the penetration level increases, as you introduce more and more of these, and the problems that we have seen in Hawaii and other places, and California as well, when the penetration level increases, the power system becomes weaker and weaker from at the point where you couple these devices. And that's what causes instability. So unless we carefully address these things, as the penetration of these renewables increases, there will be more and more challenges. And instead of helping the system, making it more reliable, we will have more outages. So that's a good area for which needs further development. So coming towards the end, if you look at the current system, for example, if you install rooftop solar, we have the distribution transformers at this end here, and we have a one-way meter, but we have all these power electronics components to connect the storage. It may or may not have the storage, and then another power electronics to connect the solar panels. Now, with AC systems, there are synchronization issues. Then when you can go from grid connected to islanded condition or microgrid condition, and then again, you have to make sure during these transitions, everything remains operational, at least on the user side. And traditionally, these transitions between grid connected and islanded depends heavily on communication links, so which increases cost and also introduces vulnerability. If the comm links or communication links get damaged or broken or not functioning, then also you will not have a reliable system. And also the question comes then, who owns these questions are coming now. Who would own the components? Is the homeowner going to own all of the solar panels and the batteries? Or could the utility own that? Or could there be a third party in between who could own that? So all these ownership issues also come in. Because as you introduce more and more of these to make the system reliable, the cost goes up. So we can think of a future systems like this, the Freedom solid-state transformer-based system, where we can have both. So we have the AC bus as well as the DC bus. The storage can be owned by the utility or a third party, and the solid-state transformer would provide power and connection to these renewables with much fewer electronics in between. So the coupling with the DC bus, when we don't have to synchronize with the AC the current day, it makes the controls and other things much more easier. And from the customer side, you can have more reliable power at a lower cost. And utility can also use the storage for other purposes like frequency regulation or peak shaving. And many utilities are interested in owning that asset. So but in the future, we don't really need that AC component in there. We can go completely into a DC-based system, like here, using the power electronics. So one other concept along those lines is emerging is like, we talk about DC in homes. We can also talk about DC for other customers. So there is this notion, thinking going on of offering by the utilities a DC as a service. So DC could be fed like to the homes where you would have these electric vehicles and solar panels, or a larger unit of these power electronic devices can be providing DC power to a customer, which could be the equivalent of a gas station where you have these charging ports, or electric vehicles or other motorbikes, e-bikes could get power from. Or it could go to some other customer who can utilize the DC. So these are the things that we expect to be evolving in the near future. So I talked a lot about the about the research and the technical. In our center, it's not just developing technologies. We have to develop the workforce also, because the industries need those trained expertise. And we have several programs, like I mentioned earlier, starting from pre-college all the way to college programs. One particular one I could mention here is the MS in Electric Power Systems Engineering, which is a professional master's degree. This is after bachelor's, where you get a master's with expertise in electric power system engineering. And this is also offered online, so it can be taken from anywhere in the world. So here is some picture of our facilities, like the lab that we use for research and training. And we have 40 kilowatts of rooftop solar panel in our building that is integrated into the power system of the building, and we actually use that to offset the electricity purchase from the grid. And these are the list of our industry members, and some of you may know some of them, like ABB is a big power component supplier. Duke Energy is our utility, an integrated utility that owns generation, transmission, as well as distribution. And then we have these many other companies here in 3 categories of membership, like the full membership, associate, and affiliate memberships. So that's all I had to say. Thank you for your attention.